Hello everybody, my name is Casey Benson. Today I'm going to be talking to you about a topic in relational database engineering that is frequently used but rarely fully understood, and that is database indexes. Some people vaguely familiar with the topic will say things like it speeds up queries or something along those lines, but how is that really done? That's what we're going to go through today. So a few prerequisites here to get a better understanding of this talk. A high-level understanding of what relational databases are is great. A beginner's knowledge of querying a database with SQL will help you. And again, a basic understanding of data structures and evaluating performance of algorithms in computer science will also be a little bit helpful here. So we're going to start with a pretty high-level question. How does a database engine find a record? So I'm going to give you an example database table. So this is a students table. So there are three simple columns here. There's an ID, which is just like an auto increment. There is a name for the student's name and their net ID. That's basically it. And then I want to ask the question, how do you find the name of a student that has the net ID jsmith1? So in SQL terms, if I were to ask this question, it would be select name from students where net ID equals jsmith1. And then looking at the table to the right, we can pretty plainly see that the answer to this question is Jane Smith. So that's easy enough, but how did we actually get there? With our like human minds, we can look at this and easily see, oh hey, at the bottom there, net ID jsmith1. That's the correct row, so the name is Jane Smith. But the database engine isn't like a human brain, obviously. So what it's going to do is it's first going to go to the first row. It's going to say, hey, is the net ID jsmith1? K Johnson 1 is not, so we're going to move on. J Doe is not, so we're going to move on. And we're going to do this again and again and again until we find our answer. So we eventually get here. We get jsmith1. And we find that the name then is Jane Smith, so that's great, we found the answer. But it took us, in this case, 2 million operations to get here. We had to go through every single row before Jane Smith until we got here. That's not great. If you're familiar with evaluating the performance of algorithms in computer science, you can probably see that this is done in ON time, meaning for every additional row to this database, we can expect one additional operation in the worst case scenario. So for a table with 2 million rows, worst case scenario, it's going to take 2 million operations. So that's what's called a full table scan. And to get a better understanding of this, I'm going to give you an analogy. So imagine a history textbook that has 1,000 pages in it, and I want you to find all the mentions of Australia in this textbook. How would you go about doing that? The quote-unquote work hard approach would be to open up to page 1, read the first word, you see whether or not it's Australia. If it is, you're going to take note of that page number. Otherwise, you're going to move on and read the next word. And you're going to keep doing this for every single word in the textbook. Obviously, that's not what you would do. You know how to work smart, so you're going to open up to the back of the book and you're going to look at the book's index. You're going to find the entry for Australia, and then you're going to take note of every page that's in the index. So essentially all the work you had to do was just go to the index and then find Australia in the index. And then you had your answer. So on the left, that's equivalent to a full table scan, where on the right, this work smart approach, that's equivalent to an index scan. So what does this actually look like in a database? So there are a lot of different approaches to indexes. I'm going to go over the one that is the most common, and that is a B tree. So essentially, again, if you're familiar with computer science and some common data structures, this will look familiar to you. But essentially, the index is composed of this graph where we have a root node, and then children of that node that eventually point to the actual pieces of data that we're looking for. So this is imagine this is the index for a new table where it's a table with 3,000 rows, and I want to find the row with an ID of 1568. Without this index, we would be back to square one, where we check the first row, see if it has the correct ID. If not, move on and do that 15,068 times until we get the right answer. With this index, though, we can work smart. So we're going to start at the root. We know we're looking for the key 1568. And so in this index, we have each node organized with 3 children. That's not always the case. That number will vary, but in this case, it's just going to be 3. So we have 3 options to go from here. We can either go left for 1 to 1,000, we can go down the middle path for 1,000 to 2,000, or we go down the right path for 2,000 to 3,000. Since we know we're looking for 1568, we know we're going to move down the middle path. So this is a new index node that will point to further children. In this case, the blocks of data are small enough that we can directly point to the data. So 1568, we can then take down this middle path again, which will lead us to the block of data with the block of data in the range of 1334 to 1666, which obviously contains 1568. And there we go, we have our answer. So all in all, that took us a total of 3 operations, even though the data set was 3,000. So what that is, again, if you're familiar with evaluating algorithms in computer science, you will see that that gets done in log n time, meaning as the database, the set of data grows, the amount of operations that we can expect the query to take will only grow by the log of that value. So does this come for free? Not quite. So if we go back to the textbook example, what's the cost of an index on a textbook? It literally adds pages to the book, so there is the cost of the paper itself. When the book is published, the index needs to be compiled by someone or something, so all of that hard work needs to be done on the front end. And then lastly, if we're going to publish future versions of the textbook, we need to update that index. So it's kind of a similar idea for the database. The index takes up space on disk, so when we're running into issues of running out of space for our database, indices are a cause of that as well. So we can't just go ahead throwing an index on every single column and every single table, because that is a surefire way to run out of space in your database. Similar to a book, when an index is added, all of that big B tree, it needs to be built, which does take a little bit of time. It's not horrible, but it is a slight consideration. And then furthermore, when a table is updated, we need to update that index too, to make sure that the B tree is balanced and that everything is still in order. Luckily, that's handled by every database engine out there, and that's not really a concern of the database engineer. So to wrap this up, when should we use an index? You know, it's great, it speeds up queries, but there is that cost, namely of space. So simply put, create an index for a column when that column will be queried frequently. That's putting it in simple terms, but that's a great rule of thumb to go off of. If you are going to query a column very often, then you should probably have an index on it. So if we go back to the example of the student table, we're probably going to be querying that net ID column very often. So we should probably have an index on that. Whereas maybe we're not going to be querying the name column directly very often. Maybe we're always going to be querying the net ID, so we wouldn't need to index the name column. That's kind of the general idea. That's about all it is. Obviously, there's more to it than that, but I hope that helps you kind of get a more high-level understanding of at least how an index is working behind the scenes. Thank you very much.